We are going to now talk about parametrizing surfaces. Okay, we've got to set up really for the long game here. So just to review kind of where we've been so far, we've looked at the line integral of a scalar function, or a scalar field if you'd like to call it that. So we've had integral over c of f of x comma y. Let's just go with a function with two input variables. Three input variables would be very similar. Okay, ds. We've seen that this converts to an integral, a t integral from t equals a to t equals b of f of x of t comma y of t, and then root we have here dx over dt quantity squared plus dy over dt quantity squared dt, with the key thing that the x of t, y of t, and of course taking the derivative of x and the derivative of y, all of this relies on the parameterization. So x of t, y of t, let's just maybe point out here where c is parametrized by x of t, y of t, with t going between a and b. The other key thing we've looked at is the line integral of a vector field. So while there's a connection between line integral of a scalar function and line integral of a vector field, just best to think of these as two different things. So we had an integral over c of vector field f dot dr was just the notation, but then how did we actually implement and compute this? Generally speaking, if you don't have a conservative vector field, what we've had to do is look at f of r of t, and you end up dotting that with r prime of t dt, and t again goes from a to b. So again here we have where c is parameterized by r of t, and r of t is just a repackaging. It's the vector function way of rewriting the x of t, y of t. It's the same kind of data that was over there, and you have here t going from a to b. I hope what's been seen very clear from both the line integral of a scalar function and the line integral of a vector field is that both of these, so the two are set up differently. Yeah, these two types of integrals are set up differently. You can see especially like key difference of the radical versus the dot with vector r prime of t, for instance. So these clearly are set up differently, but both of these things required parametrizing the curve C. So however C was described to you, whether it was a picture or in words or whatever, you would have to parametrize. And it really goes without saying that both kinds of integrals couldn't be done if you didn't know parameterization. Now we're going to move on to parameterizing surfaces. Yeah, this is going to be the new topic. But let's just point out, before getting to integrating over surfaces, which is called surface integrals, we've got a lot of work to get there. So just to outline where we're headed, it will take us 4 full class days. Today's class day is included in this, okay, to describe surface integrals. So what's a surface integral? It specifically is a topic for next section, but the point is, before we even talk about surface integrals, we have to talk about surfaces alone, and we have to talk about parameterization of surfaces for 2 days, today and the next day, and then we'll spend another 2 days on surface integrals. Really, it's just the author's helpful way to break down one challenging topic into 2 separate sections, and each of the 2 separate sections we're spending 2 days on. So given let's describe a little bit what's going on with surface integrals, just to preview where we're headed. Okay, so the setup is that you're going to be given a function f of x comma y comma z with 3 input variables. And then the second thing is you're also going to be given a surface, capital S, and that will be in R3. It'll be a certain subset of R3. So you've got a shape in three-dimensional space, which is a surface. And so, yeah, you're given a surface. Let's just do this. You're given a surface, you're given a function. These are two separate independent things you're given, and then we're going to make sense of the integral over the surface of f of x comma y comma z d capital S. There's a lot of details to get into regarding what this means, how it works, how to set it up, and all that. But we're not going to get into the details of this right now. Let's just make the comment that I cannot graph f of x comma y comma z. I mean, I cannot, because nobody can, right? You cannot, I cannot, we cannot, because there's 3 input variables and 1 output variable. So all we can do, really, all we can hope to do is do the following. But in the input space, so only looking at, the input space or the domain, which is a 3-dimensional space, so looking at R3, we, generally speaking, just try to give a picture of what we're trying to talk about here. We'll just draw, just the input space, x, y, z. So every single point in 3-dimensional space, x, y, z, for instance, being 1, 2, 3, f of that is going to be a number. But what we're going to do is inside this space, let's say there's this surface here. So, it could look like something like this. Maybe it's, something like that. Maybe it twists kind of on itself like this. So this is imagine like, this is like a stick of gum, I guess, but it's been twisted a little, right? You can sort of see the twist occurring right here because it looks like it's kind of bending under itself. A stick of gum, unfortunately, has some thickness to it. So imagine completely thin. And what we basically need to do is just pick up. So if this is the surface, shown in red here, capital S, then we pick up values of f of x comma y comma z at each x comma y comma z, which is in S. Okay, so in a nutshell, that's what a surface integral is going to be. Just to talk about where we're headed, and how do we do this? Well, like the line integral over C of f of x comma y d lowercase s equaled integral a to b of f of x of t comma y of t times root dx over dt quantity squared plus dy dt quantity squared dt. Just like this. This integral that we are talking about up here, double integral over the surface S of f of x comma y comma z d capital S now, is going to end up becoming a thing that looks like this. It'll be integral over d of f of x of u comma v comma y of u comma v comma z of u comma v, with some additional details here. Let's not worry about this for later, okay? And then a du dv there. With the thing that we should point out is, just like earlier the x of t, y of t, going right back up here, was just the way of describing a parameterization, yeah? And so we're going to have the same sort of feature going on, where x of u comma v, y of u comma v, z of u comma v. Okay, so just to point these out, where this capital S, which appears right here, it's this shape that we've got going on there in red, is parametrized by x of u comma v and y of u comma v and z of u comma v. All right. So I think it should go without saying that the beginning of the semester we spent a lot of time just talking through parameterization because that was super important to focus on. You can see that line integrals of both scalar fields and vector fields would be impossible to set up if we didn't get ourselves comfortable with parameterization. Well, we are going to need to set up integrals that look like this, and they're going to turn into integrals that look like this, right? So just like our line integral turned into this and required us to work with a parameterization, we are going to do the same thing with surfaces. What's the point then? It is important to note that since we're parametrizing here, do not blow off a surface parameterization or parameterization of surfaces. We absolutely have to know how to parameterize surfaces. So that's really the only goal of today, and the next day is just to work on that. So let's talk through this and compare it to parameterization we already know. So instead of using t, just a single variable as the parameter, we use both u and v for the parameters. It's a surface, where in the past our parametric curve was an object that was one-dimensional in nature. Now a surface is two-dimensional in nature, so we're going to need two parameters. Yeah, so use u and v for the parameters. And then same sort of deal, instead of having t between a and b, we're going to now need we now have a set D, a set called capital D. That's what, forgive me for scrolling back, this capital D right there is. Okay, so we now have a set D in the UV plane. So that's meant to mimic the T goes from A to B. Now it might not be just U and V go from constant to constant and V goes from constant to constant. You can just have any shape in the UV plane, right? And this set is called the parameter domain. Okay, so in the past we just called like A and B the endpoints or the the starting and ending values, starting and ending t values. And we used informal language like that, and we didn't have to do much because when you just have one variable, all you have to do is say what constant you start at and what constant you end at. But now that u and v are in a two-dimensional space, maybe your d is the shape is wacky enough to look like that, right? So in two-dimensional space, there's just lots more ways you can move around. So we can't just expect u and v to always just be bound by constants. And how do we obtain the surface? So just like over here, you let t take on every value between a and b, and then you get an x of t, y of t, and those form together the points. Every point is of the form x of t comma y of t. Now what we're going to do with the surface over here, same general idea, is that we let u and v take on all values in the parameter domain. This might seem a little iffy, and you might need to come back to what this means. I'm going to call an audible, actually, and just say it the following way. If you've seen some set notation, I've been trying to avoid it, but you might feel that this is more comfortable. So let me just say it this way. So the parameterization, x of t, y of t, t from a to b parameterizes the shape, the curve, capital C equals the set of all points of the form x of t comma y of t, where t runs between A and B. Okay, if this set notation is bothersome to you and you're not quite sure how to interpret it, don't worry about this too much. I'm just trying to provide hopefully a helpful way of describing this. And then what we're about to look at is the parameterization x of u comma v, y of u comma v, z of u comma v, and then the thing that replaces this is now instead the set D and D the parameter domain. Okay, what this will do is this will parameterize the surface. We tend to use a capital S for surfaces. So this is the set of all points in three-dimensional space of the form x of u comma v, y of u comma v, z of u comma v. Okay, there's the point where the point uv in its two-dimensional space belongs to the set capital D. Okay, so we will work to understand what this really is doing. Again, not so much in this notation, not with this set notation, but we'll try to make sense of this. And basically what we're doing is we're going to just be practicing. What we're really doing is the parameterization is described over here, and we'll just be taking a surface, a certain shape that is a surface, and then we will be practicing how to do this. That's what all of today's stuff is for, and that's what all of what we look at tomorrow is for as well. And that will set us up for the topic in the next section.